Okay, thanks, Mike. Welcome everyone to our seminar series. I'm going to hand it over to Mike Scarpulla from University of Utah, and he will get started. Thank you.
Okay. Well, I'm very pleased to present this. I had a very nice visit in 2015, I believe, down to CSU, and at that time I talked mostly about some defect spectroscopy we had done on CdTe-based thin film devices. Today I wanted to share some stories from the other side of my group, the sort of processing side. And in that side, we've done a lot of laser processing, particularly with cadmium telluride in the recent past. And then at the end, there was some interest in seeing some of the capabilities of my group because I had reached out to Sandpath and Jim sites about doing some experiments. So we can sort of break after the technical talk, and then those who are interested can stay and look at that part. Okay, so what I'll talk about in CAD-TEL was done in conjunction with Chris Ferrikides' group under the auspices of the Bay Area Photovoltaic Consortium. So thank you to them for providing the funding, and thank you to Chris for providing samples and guidance. So I said this. So cadmium telluride has been very successful in terms of having very near to ideal current collection, but in the open circuit voltage, CAD-TEL is well behind where we'd like it to be. So this plot shows CAD-TEL in comparison with other thin film technologies, and we can see that there's a very large voltage deficit that we'd like to solve. So some of the processing that we attempted, as well as the characterization techniques at the end that I'll mention, were aimed at improving that VOC deficit. Now, I heard a beep. Does that mean that there was a question, or is that another issue? Because I can't actually see the conference thing while I'm doing this presentation. Okay, so Jonathan, how about if I need to stop, please do interrupt if I miss something. I don't mean to just bowl over people's questions. Okay, so my group has worked for pretty much the whole time I've been here at Utah, since 2008, using laser processing to modify both SIGs and cadmium telluride materials for thin film photovoltaics. So I've listed a whole bunch of papers, and I'll sort of point particularly to the one in bold, which is a review paper that my last postdoc wrote in 2015 that contains an overview of most of it. In today's talk, I'll focus primarily on the middle section of ultraviolet nanosecond pulsed lasers used to treat the back contact of cadmium telluride. So, many of you must be familiar with the cadmium telluride devices, and there's still problems with forming back contacts reliably with low series resistance and ohmic properties. So we took on the idea of trying to use ultraviolet nanosecond lasers to modify that back contact. And we would be looking at sort of inserting such a process in the CAD-TEL fabrication process flow right there at about steps 10 and 11, where you're done making the absorber and you're doing and you've already done the CAD chloride activation, and then just before putting the final layers on the back contact. So it'd be a processing step before the final back metallization. So figure down in the bottom left shows the the problem as formulated by Jim Seitz' group. If you have a blocking back contact or a shocky back contact, it can cause rollover in the first quadrant, and in some cases decrease VOC as well as just adding a series resistance. One way to explain what's going on with CdTe is that it's very hard to find a metal with a work function deep enough to make an ohmic contact to cadmium telluride, although of course we all know that interface states play a very large role, so this simplistic picture of energy band lineup probably doesn't capture the whole physics of what's going on. So let me take this actually in a different order here. So we looked at a process like this where we'd come in with a excimer laser. The reason we chose the excimer laser is because they have short wavelengths, and they'll be absorbed very close to the surface, and therefore you won't disturb the rest of the cadmium telluride layer, which presumably you've optimized the process for already. And so if you unintentionally heat that layer or otherwise disturb it, you'll probably make things worse. So we realized through some literature searching that the vapor pressure of cadmium above heated cadmium telluride is actually slightly higher than that of tellurium. And so we figured that if we irradiated cadmium telluride surface with such a ultraviolet pulse, we should probably eject some more cadmium than we did tellurium, and that would result in a net formation of cadmium vacancies, or another way you could look at it is the formation of a tellurium-rich surface, which is prerequisite for most ohmic contact formation processes. So we first modeled this process using COMSOL finite element modeling, and most of the simulation is very straightforward heat flow, although we also added in the evaporation boundary condition as well as radiative heat loss to make it more realistic. And because we incorporated that surface evaporation term, which has some vapor pressure constants and then the flux of leaving species, we could actually predict the numbers of atoms lost as a function of the pulses from the ultraviolet laser and the energy density in each pulse. So on this chart, I've highlighted this region of interest in which you can see at least a factor of 10 in the contrast between the tellurium and cadmium fluxes, and that turned out to be pretty close to where we experimentally found good results. Okay. Okay, so we went and did the experiments, and we found, of course, X-ray diffraction picks up, it penetrates through a large distance, but if you do grazing incidence X-ray diffraction, you can pick up a very, very weak signal from tellurium being formed at the surface. We really started looking at this in a lot of depth using more surface-sensitive technique, X-ray photoelectron spectroscopy, which is really sensitive to about the top, just the top nanometers. And what's being shown here in the red and green are the components. You can actually resolve the spectral components of atoms bonded to different other atoms. So we could tell the difference between tellurium-cadmium bonds and tellurium-tellurium bonds. And after we did this laser annealing, we saw first a large shift from a peak centered at about 565 electron volts over to about 561. That first large peak shift is attributed to the reduction in surface charging. It turns out that the tellurium-rich surface conducts better than the cadmium telluride, the stoichiometric cadmium telluride, and so we had sort of a qualitative sign that the tellurium richness was formed. And then secondly, there was some asymmetry and shape change induced in the post-annealed spectrum, which you can see the red dashed line does not fit that black data, and we needed to add in this elemental tellurium peak in order to fit that with the blue line. And that was also evidence of this tellurium richness forming. So those were chemical signatures. Let's get down to brass tacks. Did it really make any difference? So we worked pretty hard on this, and we actually, I include this figure to illustrate that we actually went to the trouble of using a fib to isolate the TLM pattern that we used here. So those trenches were dug to electrically isolate this transmission line measurement pattern. And you can see that when we did that in the blue graph, we got a nice linear plot of total resistance versus distance between the electrodes. And from that plot, we can get the slope being the sheet conductivity, and then the intercept giving you twice the contact resistivity. So on this plot is plotted the contact resistivity as a function of excimer laser energy density per pulse. And we're talking about a single, each of these experiments represents a different sample area that was exposed to a single excimer laser pulse, and then a TLM pattern was made and measured. And actually some multiple TLM patterns were used in order to give us the statistics that give us those error bars. So you can see around that value of 40 between 40 and 50 millijoules per centimeter squared, we really see a very drastic change in the contact resistivity. It drops by at least a factor of 10, a factor of 20 from the untreated value. So this was a nice indication that we were reducing the contact resistance. That we then transferred this over to actual cells, and in this process we were having Ferracudes mail us samples, vacuum sealed, and then we'd do the laser annealing and then vacuum seal them back up and send them back to him. And then he completed the cells here, or his group did, I should say. And just to illustrate in real life what Jim Seitz' group showed in theory in that earlier slide, you can see if we don't do this laser, treatment, the rollover of the JV curve in the first quadrant occurs in the blue, and then once we did this laser annealing treatment, we see this green curve in which that's been eliminated. So we investigated this as a function of number of pulses, and also with and without copper, and not too surprisingly, the samples in which we added a very thin layer of copper before we did the UV laser treatment behaved a lot better. As you can see here, the fill factor is a major factor here, as well as some JSC difference. Okay, before I go on to the next part, which is diving a little deeper, I want to actually go back and show some other results here. I'm gonna show both some processing as well as characterization in this series of slides. So we had already done this ultraviolet, UV pulsed nanosecond set of experiments. And then we used a continuous wave 1064 nanometer laser. So 1064 nanometers is actually sub-band gap in cadmium telluride, but we realized that you could couple in quite a lot of power into samples that contained that were defective. Basically, if you have imperfect cadmium telluride, it offers quite a few states in the band gap that can absorb, that can participate in photon absorption and thus heat generation. There may also be some generation from other layers in the stack, for example, the TCO, etc. For characterization, we used surface photovoltaic spectroscopy. And I want you to think about this, without going into the nitty-gritty details, I want you to think about this as sort of a spectrally resolved VOC measurement in which you can measure VOC without, like a non-contact VOC. So we're actually using the capacitive coupling between the sample and a transparent conductive oxide layer on a separate piece of glass. We bring that separate piece of glass into very close proximity to the sample surface, and that capacitive coupling can let us read out the photovoltage developed by the sample. So it's a neat technique that can give you some information about your sample even before you've put on that back contact. So the geometry looked like this. We're measuring that voltage across this air gap on samples that we either did or did not irradiate with 1064 nanometer light. So on the right-hand side there, you can see the black trace is the modulus of the surface photovoltage signal, and we're actually doing this with a chopped light and a lock-in amplifier, so we can get the in-phase and out-of-phase component as well as that phase angle. So we transferred this into the modulus, and the fact that there's a little dip just above 1.5 eV actually is indicative of the signal changing sign. So we're getting a phase shift above that energy. Of course, that energy corresponds to the band gap of cadmium telluride. So we can thus conclude that the sub-band gap signal between, let's say, 1.35 and 1.5 eV was coming from something other than band-to-band absorption, and we showed in the paper that was due to some defect-related absorption at the front surface. So the oh, I'm sorry, excuse me. I misspoke that. The signal was due to the junction formed by, or the depletion width formed by the surface states at the free surface, which we usually call the back surface. And because its direction, its electric field direction is opposite to that of the main cadmium sulfide, cadmium telluride junction, its phase was reversed. I'm sorry, I misspoke there. So this picture illustrates that point. When we're in long wavelengths or sub-band gap, and just above band gap, the light is penetrating into the sample and reaching, or at least some of the carriers from that excitation are reaching the main heterojunction, the cadmium telluride cad sulfide junction, which is illustrated here by SCR2. So you get photovoltage from both of these space charge regions, and their voltages subtract because their E fields are pointing in the opposite directions. Now, in the case of blue light, well above band gap light, you're only getting carriers, the carriers modifying and producing a photovoltage in that SCR1, which is at the free surface. And so in the non-laser treated case, we saw a lot of modulation in the blue there, and of course that had the opposite sign as that from the SCR2 region. Now in the laser treated case, let's hypothesize for a minute that we got rid of the surface Fermi level pinning that's causing that SCR1. So if you have an unpinned surface, there's no band bending, and you wouldn't expect any photovoltage from that SCR1. So all you should see then is the SCR2 component at wavelengths such that the carriers can reach that deeper junction. So especially at longer wavelengths, right around the band gap. And so that was the picture that we used to, the hypothesis that we worked on to explain this. We see the elimination of that cusp in the signal, which corresponds to a phase angle shift of almost 180 degrees. And that red signal is indicative that there's only one space charge width responding. So we then also did some low temperature photoluminescence shown on the left. So this was right around, the sample in our setup sits around 13 Kelvin on the cadmium Telluride surface itself. So the major features here, the A center peak at about 1.45 eV was increased with the laser annealing, and then we saw some reduction of a lower photon energy donor acceptor pair, which we suspected was occurring at the surface. We also did some time resolve PL at low temperature, and there's arguably a moderate increase in the minority carrier lifetime there, although it's not a huge change. Okay. So in both cases, both with a continuous wave laser and with a pulsed ultraviolet laser, we were able to modify this cadmium Telluride free surface, which is then contacted to form the back contact. The next few slides talks about a very interesting deep dive we took into the science of that back contact, and this is something I'm currently still working on and pretty excited about. So the original work here has kind of led into a new new avenue of investigation in my group. So we had done that. We had done this XPS, which I'll remind you of the slide here. There it is. Okay. And then we did angle resolved XPS. So the data on the right plotted in the blue triangles and the red star were the angle resolved XPS results. And what you'll notice here is, let's just look at the yellow region there. What it says is when you quantify the XPS, it says that the surface is actually cadmium rich. And remember, the whole point here was to form tellurium rich surfaces in order to form ohmic contacts. And we have the sort of empirical evidence that we formed ohmic back contacts, which as far as most people have ever tried, doesn't happen unless you have a tellurium rich surface. We also had other evidence from a few other sources. So this was very strange. How can you have a cadmium-rich surface but still, or at least an apparent cadmium-rich surface according to the XPS, but still have that ohmic back contact? And so my postdoc Brian came up with a hypothesis or a model that was pretty compelling in explaining this. So the schematics of the model are over on the left here, and he said, okay, well, what if most of the area of the sample is actually covered with a thin layer of cadmium, and in hindsight, when you hit the surface with a ultraviolet nanosecond laser, you probably, and as we said, we were probably blowing off some cadmium into the annealing chamber. Some of it will probably recondense as the surface cools. So this orange layer probably recondensed from the vapor. Now at grain boundaries, which are shown in the little valleys in between the grains in the model, we said, hey, at those grain boundaries, maybe we lose even more cadmium than we do everywhere else, and you end up with these little pockets of tellurium richness. So the model turns out to work really well. This three scenarios we simulated here. Basically, you can't get the model to work unless it looks something like this hypothesized picture in cross section on the left here. Those black lines were the black line going through the experimental data was the best fit, and it said that the regions very close to the grain boundaries, basically only a few tens of nanometers laterally around the grain boundaries were enriched with tellurium. So that kind of suggested to us that maybe the ohmic contact was actually being made in these samples, at least, at these grain boundaries, not over the entire surface. And I will point out that that's probably a particularity of this laser processing. I'm not claiming that that's what happens for all standard processed cadmium telluride. Okay, so that got us thinking, though, about composition and grain boundaries and doping. And of course, you're probably, many of you are familiar with, there's many EBIC results and KPFM results that suggest that these grain boundaries in CadTel are probably type inverted or possibly type inverted, so that the bulk absorber layer would be low doped P-type, and then these grain boundaries may even either they have a lot of traps in them and the Fermi level is pinned more towards the middle, which would be partial inversion, or they're actually doped N-type by the chlorine donors. So this has been recognized for a long time that this could offer some benefits in terms of charge collection, which of course would give you very nice EBIC pictures. But it's also been recognized that if you have these charged grain boundaries, you're going to have a lot of recombination, and at VOC and close to the maximum power point, you're probably going to lose efficiency. So I started thinking about that maybe you can have your cake and eat it too if the grain boundaries are not uniform along their length. So we showed one particular example of how the region near the back contact along the grain boundaries could be modified in composition with respect to the bulk of the grain boundaries by doing this laser treatment. But that's maybe not the only way you could do it. So we're currently investigating this. The right-hand side is a conceptual drawing that I made of what the band diagram might look like. So you see the main junction, the Cad sulfide heterojunction has the main band bending in it there. The grain boundary runs sort of from lower left to upper right, and it presents a potential that's attractive for electrons. But then near the back contact, what if we induced a local doping or local composition such that the energy band diagram presented a reflector for those electrons at the back contact. So you can collect those electrons throughout the main thickness of the film, but right at the back they get turned around, sort of like a localized minority carrier mirror along the grain boundaries. So I'm currently working with Anna Konevcha at NREL on simulating this concept and seeing if there's any real benefit to it in terms of implementing it with realistic doping and achievable doping and parameters. But we also asked the question, does this happen in other types of CdTe, other processes of CdTe? So a few months ago, we took advantage of the new Joule scanning TEM with enhanced EDS capabilities that we got here at the University of Utah. At the time we bought it, it was one of two in North America that had these kind of capabilities. And the evidence is right there in front of you. This is a sample that was prepared according to Chris Ferricchidi's standard recipe. So it was CSS deposited and then etched at his sort of optimal etching time with bromine methanol. And what you're looking at in the left are pixels which showed Tellurium rich, that showed that the pixel contained composition that corresponds to a Tellurium rich cadmium telluride. So it's not pure Tellurium you're looking at here. It's actually 50-50 cadmium telluride plus a little bit of Tellurium on the left. And then the stoichiometric cadmium telluride with 50-50 composition is shown on the right in green. And so what you see is around the grain boundary, and actually, sort of reassuringly at the surface, you can see this enhancement of Tellurium richness, which we all thought was present and necessary for the ohmic back contacting. And of course, at CSU, we know that they do things a little differently these days. The difference that I'd point out is that the bromine methanol clearly etches down the grain boundary over distances of maybe a few hundred nanometers. We've gone back since then, and we have a bunch of images to process that show that Tellurium richness induced by this etching does not penetrate all the way through the thickness. It's only over a certain depth that the grain boundaries become enriched in Tellurium. So composition-wise, we have essentially grain boundaries with a lot of cadmium vacancies in them, which would be, the one way to achieve, one way but not the only way to achieve sort of higher p-type doping, and that concept of in terms of the minority carrier reflector, or let's say the back surface field along these grain boundaries. And of course, after this, the copper doping needs to happen, but the presence of cadmium vacancies promotes the higher doping by copper acceptors. So you sort of end up in the same place even after the copper doping as what we suppose here. Okay, so I know I've taken some time here, so I'm going to just mention one more interesting angle that we started thinking about. As a result of the trying to get proof of that Tellurium richness, we also tried to use Raman scattering. And a very observant scientist, my postdoc, noticed that the signal actually changed versus time while he was sitting the sample under this Raman microscope. And the key factor here is that this was a confocal Raman microscope, and so the intensity of light was actually quite high on the sample. And what you can see in the image is that the A1 mode having to do with free Tellurium grows really dramatically versus time, whereas there's not much change in the peaks having to do with cadmium telluride that are somewhere that Raman shifts beyond 140 inverse centimeters. And we found some mentions in the literature of this very interesting effect, which I've come to believe in, and some others have written about it too. Imagine a cadmium atom sitting on its own site in the lattice, but it only takes a small amount of energy to displace that atom into an interstitial site, leaving behind a vacancy, a cadmium vacancy, and a cadmium interstitial. So this phenomenon has been studied extensively in larger band gap alkali halides, the 1,7 compounds, very ionic compounds, and these are called F centers. So the physics is that the recombination energy from photogenerated electron-hole pair is actually sufficient to knock an atom off site. And so, I've come to believe that this happens. And this is sort of an aside during our normal investigations, but I started thinking a lot about, the interplay between photocarriers and point defects. So this is this could be regarded as sort of a kinetic effect. But then I started working on another theory, which we recently published, that has to do with the coupling between excess carriers and defects. So this is a different mechanism, but still in that vein of photo effects on point defects. So usually in the dark, if you want to figure out how many vacancies or antisites or interstitials your sample will have, you would solve a system of equations, one for each defect, like that in the box in the upper left. So each defect has a formation enthalpy, and you're assuming that the major entropy is configurational entropy, and so you get this exponential term that looks like a Boltzmann term. Okay. You see that the enthalpy of formation has the second term in that sum is the defect energy minus the Fermi energy, and that occurs for charge defects. So you solve this massive system of equations, one for each type of defect, and you impose charge balance. And so the scientific question we took on in this paper in Scientific Reports was, well, what happens when you have steady state in the light? And it turns out nobody had ever done this before. We figured out that we could actually, regard the electron and hole quasi-Fermi energies sort of, on the same footing as chemical potentials for atoms. And if you look at the way they enter into the equation, it's very similar to the chemical potentials, which are the mu A and mu B for the A and B atoms in a compound. The downside is you've got to solve the two equations simultaneously now to get two unknowns, EFN and EFP, as well as all the other concentrations of defects. So you've got to solve the steady state carrier concentration equation, which involves the generation and recombination. And the coupling comes in through the Shockley-Reed-Hall recombination induced by each of these types of defects. So we worked out this theory on, and then did a very simple example, which we took gallium antimonide as a simple example because it has basically only one defect that matters, and it's the gallium vacancy, the gallium antisite, which dopes gallium antimonide P-type under almost all circumstances, and it sort of overwhelms low concentrations of intentional N-type doping. So there's a lot of plots here. Just look at the difference between the dark concentration, which would be the black lines, and the dark blue lines, which is the highest light concentrate. The highest light intensity or generation rate. And you can see that we're predicting here that at low temperatures, at low processing temperatures, the point defects can be suppressed by a few orders of magnitude. So we ran, we're in the process of running other calculations. Here's one for gallium nitride, and the result is summarized that if you anneal or grow gallium nitride in the presence of photocarriers or light-generated carriers, you can actually suppress the concentration of compensating nitrogen vacancies and thus get more effective p-type doping in this case. So the concentration of these compensating defects goes down. And as you can guess, I'm currently running the calculation for cadmium telluride, using numbers from first principles calculations that were given to me by Suhai Wei's group, and I can hopefully report those results at a later time. But the main prediction is that excess carriers can suppress harmful defects during processing. So we went on to try to show something like this experimentally, even though we hadn't done all the calculations for CadTel. We used CadTel as an example here, and we have some preliminary results. Although I will caution that they're not. This isn't the grand slam yet. We do have to do some more legwork in terms of repeatability and spatial uniformity, etc. But the idea was we had a tube furnace. We did the cad chloride treatment inside that tube furnace, either in the dark or with a light shining on the sample down the bore of the tube furnace. And the photoluminescence results are shown in the bottom left there. So, excuse me, the sample annealed in the dark. The black curve actually has a higher intensity of that A-center peak. And the red one annealed in the light has a lower intensity. And with that, if we think what the A-center actually is, the A-center is thought to be a vacancy of cadmium paired with a next-door neighbor compensating donor. And so, in some sense, we've maybe suppress the formation of these compensating dopants, although I'm not sure I would hang my hat completely on this result yet. There's also obviously two other features that change in the spectrum. The exciton peak in the red curve, the exciton peak at 1.55 or so electron volts becomes a little more pronounced in the one annealed in the light. Which suggests that the lifetime, the minority carrier lifetime, is at least longer. And then there's also a more pronounced separated donor-acceptor pair related peak down around 1.25 to 1.3 eV, which might suggest that these donor-acceptor pairs are staying spatially further apart rather than forming those A-centers. Okay, so let me wrap up there the summary of what we've done with laser treatment and some photo effects and point defect equilibrium, and then I'll be happy to talk about the characterization results with anyone who would like to stay. And it looks like I've run long, so my apologies to your ears for straining them for too long.
No apologies necessary, Mike. It looks like no one's typed in any questions during the talk, but if you have one, please feel free to either turn on your microphone and ask that way, or type something into the chat window.
Okay, thank you, Brian. Okay. Well, I guess I explained everything very clearly, and just the overwhelm. What is the gap? Okay, sorry. Sampath is writing a question here. What is the the gap, Sampath, I assume you mean the physical spacing between the sample and the TCO electrode. What we did is actually called soft contact. We basically had the electrode pressed up the sample in such a way to maximize the signal but minimize parasitic conductivity. And this technique can be done in other ways. People have inserted sheets of mylar or mica. You could put some kind of a self-assembled monolayer or something like that on the surface also. But we did it just with a naturally formed air gap between the two surfaces. So the short answer, I don't know how thick it was, but it allowed us to get capacitance without too much conductance. Okay, so Jason at CSU asked the question, did I attribute the tellurium at grain boundaries to your etch process? So yes, in the case of the laser processing, yes, we did. And maybe the question is about the bromine methanol samples, and we're still doing microscopy ongoing here. We did a few rounds of microscopy and control samples to see if there was tellurium richness before the etching. Please type and let me know if that answers your question. Okay, so Jason, I showed two different types of samples that were separate. So the samples that we did the XPS on were the laser processed ones, and we did not do TEM on those samples. Conversely, the samples that we did the TEM on were solely exposed to bromine methanol etching. Looks like we've got a question coming in from Kurt. Hi, Kurt. How repeatable was the laser annealing? Well, when we did the TLM patterns, it was, the error bars were shown there, and we did at least three TLM patterns for each fluence, and we got a pretty tight distribution there. Now, I think the more, the real question is how would that scale to a module, right? We're using a single pulse from a KRF laser, and we were doing areas that were millimeters in size, and our concept was that companies like Coherent have already established processes for using excimer lasers to recrystallize silicon and TCO layers for displays, up to Gen 5 displays, which is, I forget, it's like 2 meters by 2 meters or something like that. So they've perfected these optics trains that produce a 750 millimeter wide, so 75 centimeter wide by 1 or 200 micron beam with something like 1% intensity variation. So they then step that sequentially along these large display glasses. So in terms of delivering the pathway to scale up, we were arguing under this BA-PVC project that there was a pathway to scaling to CdTe manufacturing. The world hasn't caught fire. I don't see First Solar doing this right now, so I'm not sure that it's the sort of killer app that we thought it might be. Yeah, I think things like the application of the spatial variation in the cad chloride treatment might outweigh the intensity variation in the laser. Okay, so Sampath had asked that I should talk about some of the other capabilities in